What is going on, everybody? Dan Tramte here, and welcome back to my tutorial series called Browser Noise. Okay, I'll stop. I'm sorry. This is tutorial number 8, and what I want to do is I want to talk about sound propagation. And in doing so, we're going to build a sort of audio-visual animation thing that will simulate how sound propagates in space. And I don't want to talk too much. Let's just go ahead and let me show you what I want to do. Okay, so I'm going to first change our canvas to 400 by 200. So it's twice as wide as it is tall. And I'm doing that because I want to divide it in two halves. Okay. And yeah, let's run that. And let me actually go ahead and move myself. Okay. So on this half, there's going to be what looks like a circle. And that circle is going to be kind of like an engine, if that makes sense. It's going to spin, and there's going to be a spoke, and that spoke is connected to a piston that connects to a diaphragm, and that diaphragm will move back and forth according to our circular motion that will be right here. Okay. On this side of our canvas, there are going to be a bunch of particles. And those particles are going to animate according to how, a speaker would push and pull air particles in space. So let's do that. All right. The first thing we're going to do is we're going to make our air particles. In reality, air particles are sort of randomly distributed in space, but for our animation, we're going to make them evenly distributed in space. So what we're going to do is we're going to sort of build a grid of air particles. And by air particles, I mean dots, right? Okay. So there's a convention I like to follow whenever I'm building a grid of something. I like to have a variable that refers to the spacing of those particles, and I usually call it cell. All right. So we're going to go ahead and set cell equal to 20. And then we're going to drop down in our draw function, and this is where the fun starts. Okay, we're going to do nested for loops. And what I mean by that is a loop inside a loop. And just to note that those two loops are going to happen inside our draw loop. So lots of loops going on. So for x equals 0, x is less than width over cell, think about it, x plus plus. So let's think about that. Our width is 400. So imagine a 400 right here. Our cell is 20. So imagine a 20 here. 400 over 20 is 20. Yes. So this for loop is going to happen 20 times, right? Whatever code I put in here is going to happen 20 times, and the code that I'm going to put in there is another for loop. So I never put a let there. I don't think you need the let, but it's good practice to do that. Let y equals 0. Y is less than height over cell, y plus plus. And then we're going to have open and close curly braces. And so if we think about what happens in this loop is height is 200, right? So imagine a 200 here. 200 over our cell, which is 20, is 200 over 20 is 10. So this loop is going to happen 10 times. Every time this loop is iterated, which is 20 times. So 10 times 20 is 200. The code that we write in here is going to happen 200 times. All right. You might be thinking, why don't I just make one for loop happen 200 times? And that's a good question. There are ways to do that. But the value in this is that we now have an x value and a y value that we can use. So let's draw an ellipse at x times cell, and then y times cell, and then the size of those are going to be cell over 3. Let's see what that looks like. Look at that. We have a grid of particles. Now, there's something that bothers me about it. It like starts directly at 0, and then there's all this extra space on these two sides. So what we want to do is shift everything over by an amount. And what amount would make it so that it sort of sits evenly? Well, we have a cell value of 20. So whatever, and that represents the spacing between each of these dots. So we need to move everyone by half of that spacing. So we're going to add here plus cell over 2, right? And that, here, let's see that, plus cell over 2. And now when I run it, everything is nice and evenly spaced. Beautiful. I love it. Excellent. Very good. Now, if you remember my explanation, here, let me grab me. There's going to be a thing over here that drives a diaphragm, which sits in the center of the canvas, which would be about right here. And then all of our particles are on this side. So we actually need to shift all of the particles over this way to our right. So, which is my left, by the way. So in order to do that, we're just going to add another offset, and that will be width over 2 to our x value of our ellipses. And there we go. So it is true that we currently now have a bunch of ellipses that are being drawn off canvas. We can trim those later, but for now, this is going to work. I want to get beyond this point. All right. It's about to get real. We are going to start animating. Follow along. There's going to be a lot of stuff that I type, and some of it is going to look scary. We will go over it, I promise. Let's declare 2 new variables called amp for amplitude and frec for frequency, and then 2 more called x angle and y angle. All right. Whenever we are dealing with angles, there are 2 ways to imagine angles. So for example, if I wanted to rotate something, I could rotate it by radians or I can rotate it by degrees. For me, degrees make a little more sense because I like to think about 0 to 360. That really makes sense in my head. Whereas pi and 2 pi, it's not so bad. I can do it, but it requires a little bit more mental gymnastics for me. So we're going to use angle mode, and we're going to call degrees. All right. So let's set our amp to something like 20. Let's set our, well, let's do it right here. Frec to something like 0.3. That sounds like a very slow frequency. If we set an oscillator to 0.3, we wouldn't be able to hear it because that's out of our hearing range. But in terms of animation, that's going to be a nice value for us right now. Okay, here's where things are going to get a little scary. Y angle equals sine of millis, I'm sorry, times frec over 2.778. And then x angle equals cosine of millis times frec over 2.7778. Make sure that's the same amount of sevens for each. It doesn't really matter how many sevens, but okay. I know as I started typing sine and cosine, half of you were basically like, I'm done. This is not for me. I was hoping high school would be the last time I saw those 2 words. But okay, here's the thing. Sine, let's talk about what's happening here. Sine returns a number between -1 and 1, okay? That's all you have to think about sine. It's totally innocuous. -1 to 1. It's just that whatever we have driving that sine is going to be is going to determine exactly which number between -1 and 1 that sine is going to return. In this case, what is driving our sine is a little bit complicated, but let's break it down. Millis is a function that returns a value of elapsed time in milliseconds from when I first hit run. So let's actually watch what happens. If I say print and then millis like that, let's see what happens when I press play. Uh-oh, line 7, degrees. Let's try now. All right. So now if you look in the console, we have numbers that are in the thousands and they keep climbing. So right now, 7,000 milliseconds has elapsed since I first hit the run button. And we can use those values to drive our sine function. So, and then let's just very quickly look at this. Don't think about it too much. I wanted to be able to enter hertz into our frequency variable, and I did a little bit of algebra before I started recording just to figure out what I would have to divide that into in order for it to all work. So don't think too much about it. Just make sure you've typed it out properly. Okay, so now what I want to do is I want to draw an ellipse down here after our for loops, okay? Now, ellipse will take, we'll put in 3 arguments. So our first one will be width over 4, height over 2, and then we'll do something like amp times 2. I understand if that might seem like, why? What does the diameter of a circle have to do with amplitude? Well, we'll get into that pretty soon, but just to note, our x value is width over 4 because we want it to be 1/4 of the way through this canvas, and our height is 1/2 of the way. Okay, now look what we can do. The reason that I created a variable called y angle and x angle is because I want something that oscillates, all right? And one thing that I can do is take width over 4 and add our x angle, all right? This is not what we're going to eventually do. I just want to demonstrate what it looks like for something to oscillate. So let me press play. You can't see it right now because the motions are so tiny, but this circle is animating. It's moving left and right. I can amplify that by multiplying it by something like, well, let's just use a constant like 20. Look at that. Oh, that looks so good. That looks so good. Now, height over 2, let's add our y angle to that. And we'll multiply that by 20, right? So it looks like that. Press play. Our circle is animating in circular motion. Awesome. That's the whole point of doing all of this work, is to have something that's oscillating on the x-axis and something that's oscillating on the y-axis out of phase, so that it creates this circular motion. That is awesome. Okay, and now actually I don't want to animate this circle like this, so I'm just going to cut all of this out real quick. What I want to do, this is our oscillator wheel. I'll just add some some comments. Now we're going to draw our spoke, and that is going to be a line. And bear with me. Width over 4, height over 2. So the first coordinate of our line is going to actually, let's actually stop running that. is going to be drawn in the middle of where we drew this circle above. And then the other coordinate is going to be width plus x angle times amp. Okay. Height, we're starting to lose. There we go. Height over 2 plus x or y angle times amp. All right. Watch this. I did something wrong. Hold on. X width. Okay, yeah, this is what I didn't. This is width over 4. Look at that. We just drew something that sort of resembles like a clock, but in our case, it's just going to be a wheel. All right. So this is like the next line we're going to draw is, we'll call it a piston, but really what it is a bar that connects our spoke to our diaphragm. So this one's probably the most difficult one to write out. So width plus x angle times amp, height over 2 plus y angle times amp. And then for our other 2 coordinates, that's going to be width over 2. So it sort of originates from the center of our canvas plus x angle times amp. And then, oh my gosh, these code boxes are too small. Height over 2 plus y angle times amp. Okay. That's what it looks like since I ran out of room. Let's do that. Look at that. So that's a nice bar that connects from our spoke to something that's sort of circling the center of our canvas. Okay, and last but not least, let's draw that diaphragm. So that's going to be down here, diaphragm. That's how you spell it, and but that's not how you pronounce it. Width over 2 plus x angle times amp, 0. Width over 2 plus x angle times amp, and then height, and that's it, because we want it to just be a line that starts, the y value is going to start at the top and just go to the bottom, but it's entire the whole thing is going to move left and right. So let's let that run like that. Okay, look, we've done a lot today. We've done nested for loops and talked about sine and cosine. That's way too much for one video. So let's move on. I'll see you in the next one. Check you later. Bye.